Okay, so we've looked at what's going on with the electron cloud and what the current model is, the quantum mechanical model, and where these electrons are. We really don't know because they constantly are gaining and losing energy, so we just have a probability of where they are actually located. But for this section, what we're going to assume is that we're going to try to figure out the electron configuration, meaning where are the electrons or where would they be if they were not gaining or losing any energy. So I'm going to kind of show you how to do an electron configuration. We're going to practice with some examples. We have to follow 3 rules. So I'm going to go through and kind of go through these 3 rules one by one and kind of show you electron configurations as we go. So the way in which electrons are arranged in their orbitals, so we've talked about, the s, the p, the d, the f, around the nucleus. This is called an electron configuration. We're also going to look at something called an orbital diagram. And I'll explain that in a minute if you just want to write it off to the side. We're going to look and see what an orbital diagram is, an electron configuration, and a couple other things going on with these electrons. So the 3 rules that I will be following are the Aufbau principle, the Pauli exclusion principle, and then Hund's rule. You follow these 3 rules to actually do the electron configuration. So we're going to go ahead and get started. So the first rule is, it's called the Aufbau principle. So according to this principle, electrons are going to occupy the orbitals of lowest energy first. And we talked about this last time. The lowest energy, if I've got my diagram here, the lowest energy is going to be level 1. Remember, I've got level 1, level 2, 3, so on. So level 1 is the lowest energy. So level 1 is going to be filled first. So they're showing them in these boxes. If you kind of take a look at that picture, they're kind of showing them as boxes. Remember, we talked about an s orbital has 1 orbital. That's why they're showing 1 box there. When you get to a p, there's 3 orbitals. When you get to a d, there's 5. And remember, within those orbitals, there can be 2 electrons. So there can be 2 in this one, there can be 6 in that one, and this one can hold a total of 10 electrons. So I'm going to start with a really easy electron configuration. We're going to look at hydrogen first. So if you look at hydrogen on the periodic table, it only has 1 electron. So obviously, by following this rule, it's going to be in the lowest energy level first. So it's going to be in level 1. So I'm not going to draw this as boxes. I'm just going to draw it as a line. So there's my orbital for 1s. It's got 1 electron in it. So that right there is called the orbital diagram. This right here is the orbital diagram that I kind of talked about a minute ago. Not a very good D, but it'll pass as a D. So that's your orbital diagram. The actual electron configuration, the way that you write this, is you write 1s, meaning the 1s orbital, and you write it as a superscript. You're telling me that there's 1 electron in there. So let's practice with another one. Let's look at beryllium. If you find beryllium on the periodic table, it has an atomic number 4. So remember, we talked about in chapter 4, 4 protons is the atomic number. So if it has 4 protons, that also means it has 4 electrons. So following this rule, filling the lowest energy levels first, 1s can hold 2 electrons. So I'm going to show that with an up-down arrow. I will explain the arrows whenever we get to the next rule. Just kind of follow along with me right now. So the 1s has 2 electrons in it, but this element has 4 electrons total. So I need to move on. So if you look at the picture on the right there, the next orbital that's filled is 2s. And an s orbital, no matter what level it's in, can hold 2 electrons. So there's the orbital diagram for beryllium. So then the electron configuration, or what can also be called, I forgot to tell you up here, it can also be called short form. So the short form for beryllium would be 1s2, 2s2. So that's kind of an explanation right there of what's going on with the Aufbau principle. So we're going to move on to the next rule, and it's going to kind of explain why I'm doing the arrows like I'm doing. So the Pauli exclusion principle, this is an atomic orbital may describe at most 2 electrons, meaning every time I get to a line which is representing an orbital, it can have 2 electrons in it. So within that orbital, though, those two electrons have to have opposite spins. So that's why I'm writing an up and a down arrow. We can't see these electrons, so really all we can kind of show to represent this is an up-down arrow to show that they do have opposite spins. So I'm going to go back a little bit. Let's look at helium. If you find helium on the periodic table, its atomic number is 2. So that 2 represents protons, but what we're looking at in this chapter is electrons. So the lowest energy, we've got to follow both rules here. The lowest energy level is filled first, so 1s would have at most 2 electrons, and it can hold 2 electrons. You can't move on to the next orbital until this one is filled. So this electron, or this orbital, would have 2 electrons in it. So that's the orbital diagram. So then the short form, or the electron configuration for helium, would be 1s has 2 electrons in it. So let's try another one. So boron, number 5, is the atomic number. So if you understand what's going on, why don't you pause me and try to see if you can do this on your own. If not, just kind of follow along. So I've got to deal with 5 electrons. So I'm following both rules. I got to deal with 2 electrons being in an orbital. They got to have opposite spin. And I've also got to consider that lowest energy level is going to be filled first. So 1s can have 2 electrons, both with opposite spins. There's 2 of the electrons. The next orbital that's filled is 2s. It can also have 2 electrons. So there's my 4. But boron has 5 electrons total. So the next orbital that's filled is the 2p orbital. Now, when I get to 2p, a p orbital has 3 orbitals within it that can hold 6 electrons total. But for this element, there's only 1 electron in it. So my short form for this would be 1s2, 2s2, 2p1. So you can add this up. If you add up the superscripts, it should add up to your element. So it does add up to 5, so that tells me it's boron. So there's 2 of the rules down. We're going to look at the last rule, which is Hund's rule. Hund's rule is kind of confusing. It states that electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. So to restate this in a way that's going to make sense to you guys is you're looking for the maximum number of unpaired electrons. That's what you ultimately want, because for elements to interact with one another, you want those unpaired electrons in those orbitals, and that's why they form compounds. And we're going to get back into that. You did this in physical science, but we are going to get back into that. So understanding what's going on with these electrons in the very outer orbitals is important. So to kind of show this rule, what we're going to look at is oxygen. If you find oxygen on the periodic table, it has an atomic number of 8. So we're going to follow all 3 rules now and look at what the electron or the orbital diagram would be. So I'm following the fact that I'm doing the lowest energy levels first. Only 2 electrons can be in an orbital, and they have to be shown with opposite spin. And then I'm also going to look for getting the maximum number of unpaired electrons. That's really not going to come into play until I get to the very last orbital. So 1s is filled first. The s orbital can have 2 electrons. So that's 2 of the 8. Then I move on again to the 2s. We've kind of getting the same order every time. So 2s would have 2 electrons in it. So that's 4 electrons total. Then I get to a 2p. So the way that you're going to get the maximum number of unpaired electrons, and to do this correctly, what you have to do is you have to put 1 electron in each one of those 3 orbitals. And then even if you get to a d, which would have 5, you would have to put 1 electron in each orbital before you go back and start pairing them up. So I have 4 electrons accounted for right now, so I have 4 left. So I'm going to count. For this would make 5, 6, 7, and I have 1 more. So now I can go back and pair those up. This gets me the maximum number of unpaired electrons. This helps me follow Hund's rule. So that would be the electron configuration. If you did not do this, I will erase this, but what you would do is if you did not get that, you would get these two. I'm not going to rewrite that. And then if you got to this p orbital, what you would do is say 4, 5, 6, 7, 8. So it's going to look like you don't have these unpaired electrons. And if you don't know what I'm talking about by the unpaired electrons, it's that electron and that electron right there. The ones that are in the orbital by themselves that aren't paired up with one. So these are paired, these are paired, these are paired. If you did not put one in each orbital before you moved on, it's going to look like that, and it's going to look like you have no unpaired electrons. So make sure that you get that right. I'm going to go ahead and erase that, so I can use that room. So another thing that you're going to have to be able to do, and you know those unpaired electrons right there are the ones that are interacting with other elements. So it's important to understand how many, for one, unpaired electrons you have. So I'm going to put that as U and P. And then also how many valence. You learned about valence electrons last year. Can't write that. That's supposed to be valence. Okay, so valence. So unpaired electrons, we've kind of said, it's this one and it's this one right here. This element, oxygen, has 2 unpaired electrons. But if I wanted to look at the valence electrons, the definition of a valence electrons is the maximum amount, or the electrons that are found in the outermost energy levels. So right now, you have electrons in level 1 and level 2. You have to consider the electrons in an s and a p orbital, whatever outer level is. So basically, you have 2 valence in 2s, and you have 4 valence in level 2p. So you have a total number of valence of 6. You also learned a trick in physical science to look at the group that oxygen would be in, and it's in group 16, so that tells you drop the 1. It has 6 valence. So you can double check yourself. So what I want you to do is to try to work magnesium. Magnesium is number 12 on the periodic table. So if you can pause me and try to figure this out, what I want you to do is try to figure out the orbital diagram. The short form, which I forgot to do, for oxygen it would be 1s2, 2s2, 2p, 4. So I want the orbital diagram, the arrows, I want the short form, and I also want unpaired and valence for magnesium. So you can pause me, try to work it. I will work it out if you're confused. The 1s orbital is going to have 2 electrons. The 2s orbital will have 2 electrons. When I get to 2p, I'm going to say that would be 5, 6, 7, 8, 9, and 10. And then I have to move on to the next orbital, which would be 3s. That would be 11, and that would be 12. So my short form would be 1s has 2 electrons, 2s has 2 electrons, 2p has 6, and 3s has 2. So then if I moved on to the unpaired, for this element, there's 0 unpaired. Every single one of those electrons is paired up with one of opposite spin. But valence, my valence is the outermost energy level. Where are electrons in the outermost energy level? So I have level 1, I have electrons in level 2, but I also have electrons in level 3. So this right here is my outermost energy level, level 3, and it just has 2 electrons in it. And also magnesium is in group 2. So here is just an orbital filling diagram for the first 11 elements on the periodic table. It kind of shows you, they show boxes again, but they show you the orbital diagram, and they also show you the short form of the electron configuration. So you can kind of take a look at those. The actual order that it will follow. So you've got 1s, 2s. Now, it does get a little tricky because after 3p, 4s is filled. then 3D. So the definition is it fills the lowest energy levels first. So 4s has lower energy than 3D, so that's just the order that it goes. What I'm going to do is show you a periodic table and let you try to kind of figure it out. If you can read it, and I'm going to go ahead and skip to the next slide. If you can read this left to right, it tells you the order. Now, I'm going to give you a copy of this. It's hard to read it on here. These are S's right here. So it's row 1 is 1s. So this box right here is 1s. This is also 1s. So then when you move to the next row, this is 2s. Then you go to 2p, and then you go down to the next row, and this is 3s. And then 3p gets filled, and then you move to, this is 4s, and then you move to 3d. So if you can read it kind of like you read a book and left to right, and I will show you this whenever you get into class, but that is the order in which those electrons fill if you just follow left to right going down the periodic table. We will be working on more of these. Do is try to work out phosphorus. Do the arrows, do the short form, tell me unpaired, and tell me valence. And we will go through this in class next time. Also, answer the questions in your WISC form. Thanks.